Myself, Dr. K. Viswanath Allamraju, Department of Mechanical Engineering, Institute of Aeronautical Engineering, Dundigal, Hyderabad. In this session, we are going to study the revision of deflection of the beams, part 3. So far, we have covered what is the deflection of the beam. In previous sessions, we covered previous parts, part 1 and part 2. In part 1, we have covered what is governing differential equation of the beam, and what is the purpose of the deflection of the beams, and what is double integration method. And part 2, we covered by using double integration method, considered cantilever beam. And the cantilever beam, we considered a concentrated load at the free end, and that is case 1. And case 2, concentrated load is acted at any distance on the beam of a cantilever beam. What is the slope and deflection? And also UDL we considered a UDL throughout the span of the cantilever beam, and UDL is partial. The origin of the UDL begins from the fixed support, and another case is UDL acted on the cantilever beam at a distance of A from the free end. And another case is that cantilever beam is subjected to only movement in clockwise direction at the free end. And finally, the uniformly varying load is acted on the cantilever beam throughout the span of the beam. So those are the case studies. We derived the slope and deflections at fixed support and at the free ends by using double integration method. Now in this session, we are going to consider a simply supported beams having a concentrated load at mid-span, but we are going to use the double integration method. There are various methods we discussed in the previous session. One of the method, we discussed it theoretically, that one of the method is double integration. Another method is Macaulay's method. And moment area method. The moment area method is also known as Morse theorems and conjugate method, and so on. But here we are going to study how to use double integration method for calculating the slope and deflection of a simply supported beam. Concentrated load is acting on the beam at the midspan of the beam, that is at a distance of L/2. And there are two supports here, support A and support B. Support A and support B, the concentrated load is acting at the midspan of the point beam at point C. So the reactions by using the shear force and the bending moment concepts and applying the equilibrium condition sigma Fi equal to 0 and moment equilibrium equation, we have calculated the reaction that at RE and RB. Here, the equally distributed the load acted on the beam is at the midpoint, at midspan, at midpoint of the beam. So, the reactions at support A and support B are equal. That is, RA equal to RB. So, therefore, here RA equal to RB, that equal to W/2. Now, consider a section. We want a moment at a section X from left support A at a distance of X we considered. That is section A from the origin. The origin is at A. We consider the origin at A. The origin at A, then M equal to W/2 times X. Now equate this M equation with governing differential equation of the beam, that is A times d square by dx square, that equal to W/2 times X. If we integrate once this equation, we get the slope. And if we integrate the slope equation, we get the deflection of the beam at a distance of X. So that's what here we have done. The equation, above equation we integrated once, that is I times dy by dx equal to W times x square by 4 plus C1. So this C1 is the constant of integration. The constant of integration to be calculated by using the boundary conditions such a way that it should have a relation between the slope and the span of the beam, that is at x equal to L/2, dy by dx equal to 0. This is the boundary condition. Now substitute this x equal to L by 2 divided by dx equal to 0 in the above equation. We'll get the C1, that's E1 obtained as minus WL squared by 16. Now WL squared by 16, that is EI times divided by dx equal to, substitute back the C1 value in the equation, above equation, then we'll get the slope. The slope equation is EI times divided by dx equal to WX squared by 4 minus WL squared by 16. This equation is known as slope equation. This equation is known as slope equation. EI by DI times dy by dx equal to Wx squared by 4 minus WL squared by 16 is known as slope equation. The slope equation is such a way that by changing the value of the x, by substituting the value of the x, the value of the x means the span of the beam. At x equal to 0, what is the slope? The slope at x equal to 0, that becomes theta a. That theta a equal to minus WL squared by 16 times EI. Now, if we integrate the slope equation, we get the deflection, that is EI times y equal to W by 4, that x cubed by 3, that's 3 times 4, that is 12, W x cubed by 12 minus WL square x by 16 plus C2. Again, the C2 is the constant of integration. The C2 should be calculated by using another boundary condition, and that boundary condition should have a relation between, it is related to the deflection, that's why span versus deflection. So here x equal to 0, y equal to 0, EI times y equal to Wx cubed by 12 minus WL squared by 16, L square x by 16. This equation is known as a deflection equation. Deflection equation. Now the slope and deflections are derived here. That is the deflection dy by dx equal to, that EI goes, that is a flexural rigidity, goes to right hand side, and make the common term W by 16 EI. If we make it common, that is L square minus 4x square. This is minus of this dy by dx equal to minus W by 16 EI times L square minus 4x square. And deflection in terms of y, that is y equal to this flexural rigidity goes to right side, then make a common term LCM, that is 48 E48, then it becomes the L square x minus 4x cube. This is the equation of the slope. So if you want at support, what is the slope? At x equal to 0 at A, that is the origin, A is the support, A is the origin. At x equal to 0, substitute x equal to 0, what is the slope here? That is negative of WL square by 16 EI. At x equal to 0, what is the deflection? The deflection is y equal to deflection at A by A. Substitute x equal to 0. If x equal to 0 here, the term becomes 0. That means deflection becomes 0. Deflection at A is 0. Now, that's what at fixed support, the deflection is 0 and the slope is the maximum. And coming to at deflection at C, what is the C? X equal to L by 2. At a C, that is x equal to L by 2. Substitute x equal to L by 2 deflection value. The deflection is obtained as WL cubed by 48 EI. If you substitute x equal to L by 2 in the slope equation, that slope becomes theta C, becomes 0. X equal to L by 2, that is L square by 4, 4 get cancelled, L square minus L square, that becomes 0. So dy by dx becomes 0 at C. So this is the deflection at C. Point C, the deflection value is the maximum where the slope equal to 0. Alright, that is the meaning here obtained. Now slope and deflections for the portion, we consider here CB. Now CB is symmetric for AC, so it is about, we consider for AC we have read completed, but if you wanted CB, but it is symmetric, therefore the equation is same. But can also be here that CB with A is origin can also be formed in the following form, that is dy by dx equal to negative W by 16 EI times 4x square minus 8LX plus 3L square. And the deflection equal to W by 40 minus W by 48 EI times 4x cube plus 9L square x minus L cube minus 12LX square. These are slope and deflections. Now, another case we are going to consider by double integration method, that is UDL, uniformly distributed load on whole span. So, uniformly distributed on whole span, we consider the simply supported beam. We are going to use here again double integration method. Double integration method. By using double integration method, we are going to find out the slope and deflections of a beam subjected to uniformly distributed load throughout the span of the beam. Here, there are two supports A and B. The reactions we have to calculate by using the fundamentals of shear force and bending moment diagrams. By using equilibrium conditions, the reaction at A is WL by 2, reaction at B is WL by 2. This W is the load intensity, that is a small w, that is newtons per meter. Now here, considering the section, what is the at a distance of x, at A is origin here, origin, so distance at a section x, what is it, mx. The mx equal to WLX by 2 minus WX square by 2. That equate to governing differential equation of the beam, that is EI times or d square y by dx square equal to WLX by 2 minus WX square by 2. Now, again, the methodology is same. Let's begin with integration. First integration gives the slope equation, that is EI times dy by dx equal to WLX square by 4 minus WX square by 6 plus C1. The C1 is calculated by using the boundary conditions such a way that which is related to both the span, length of the beam and slope. So at x equal to L by 2, dy by dx equal to 0. At the midpoint, the slope equal to 0 because it is 0 degree. So it is 0. Substitute this apply this by applying this boundary condition. The C1 is obtained. The value of the C1 becomes minus WLQ by 24. By substituting back in the original equation, that becomes the slope equation. That is EI times dy by dx equal to WL times x square by 4 minus WX square by 6 minus WLQ by 24. Now, that is that equation is known as the slope equation. Now integrating the slope equation above equation, then the deflection is obtained. That EI times y equal to WLX cube by 12 minus WX per 4 by 24 minus WL cube by 24 times x plus C2. This C2 is another constant of integration. That constant of integration will be calculated by using the boundary condition such a way that x equal to 0 and y equal to 0. That equation is related to deflection and the span. Now the value obtained is C2 equal to 0. Then EI times, substitute back the C2 value, then the deflection equation, that is EI times y equal to WLX cube by 12 minus WX power 4 by 12 minus WL cube by 24 times x. This equation is the deflection equation. This is the deflection equation. This is the deflection equation, and here it is slope equation. EI times dy by dx equal to minus WL x square by 4 minus WX cube by 6 minus WL cube by 24. There is the slope equation, and this is EI times y. This is the deflection equation. These two equations are important in order to find out the slope and deflection values at various values of x. Now, the maximum deflection, we want the maximum deflection. The maximum deflection happens where? At x equal to L by 2. Substitute x equal to L by 2 in the deflection equation. The maximum deflection, that is obtained as 1 by EI times WL by 12 L by 2 whole cube minus W by 24 x power 4, that is L by 2 power 4 minus WL cube by 24 EI times x, that is L by 2. That value of that deflection value is minus negative of 5 W alpha 4 by 384 EI. This is the y maximum y value. Alright. Now slope at A. Slope at A. What is the slope at A? At support A. What is the slope? The deflection y equal to 0. That means x equal to 0. Substitute in the equation of the slope. The slope equation, here it is, yes. At x equal to 0, substitute here, the term becomes WL by 24 EI. This is what WL by 24 EI. So that means we considered here maximum values. The maximum value of the slope is at support A. Slope at A is maximum. What about at YA? That YA equal to 0. And deflection maximum where? At midpoint. At point C, theta C equal to 0, slope is 0, and Y becomes Y maximum. So these are the maximum values we calculated, maximum slope and the maximum deflection. So where the maximum slope at points at fixed support, the slope is there at fixed at support A, there is a slope, but the maximum, the deflection is 0, it is the support means no deflection. But at the midpoint, that where x equal to L by 2, the deflection becomes Y maximum. Y equal to maximum value, deflection is maximum. But what about slope? The slope becomes 0. So in this manner, we calculated the slope and deflections of a beam, simply supported beam, subjected to uniformly distributed load throughout the span of the beam. So these are the formulae derived for this particular cases. Suppose if we consider if the partially applied load at a distance from left support, at a distance of A, UDL is acting, is the UDL, is support A and support at B. What is the slope and deflection? Yes, it is entirely different. It is changes again. We have to apply, go for the methodology, you have to go for what is the, at a distance of x, what is the mx, and equate that mx to governing differential equation of bending beam, that is I times d square by dx square, and do it first integration, gives the slope. The slope equation consists of the constant of integration, that is C1. C1 should be calculated by using the first boundary condition. The boundary condition should be related to span of the beam versus the slope. From that, substitute calculate the C1 value. The C1 value substitute back in the equation. That equation gives the generic equation of a slope. And again, integrate the slope equation, then deflection equation comes. The deflection equation consists of constant of integration C2. The C2 should be calculated and substitute back in the deflection equation. That gives the governing equation of the deflection for this particular case study. In this manner, we have to follow it. Now, in the next case study, here it is the couple at one end. Couple at one end, that means at left side it is in clockwise direction, at left support A, is the support B. The span of the beam is the L. How to make it? By calculate the reactions at A and B. So we consider the reaction at B, that is RB equal to M by L, it is in upward direction, whereas RA equal to M by L, it is in downward direction. Now after changing the notation, is downward, RA equal to M by L, and RB equal to M by L upwards, it is in clockwise momentum. Okay, it is in clockwise, it's completely balanced now. Now here what to do? Again, couple at one end condition, equate that moment equation at a distance x, that is I times d square by dx square equal to minus m by l x plus m, because more couple is acting in clockwise direction. Now if we integrate this once this equation, if we integrate the first the differential equation of the moment equation, that is I times dy by dx equal to minus m by l x square by 2 plus mx plus c1. That c1 will be calculated by using again boundary condition. Constant of integration should be calculated by using boundary condition. Now here integrate again this slope equation, that is ei times y equal to minus mx cube by 6l plus mx square by 2 plus c1x plus c2. Alright. Now substitute at a, what is at a? At support a, x equal to 0 and y equal to 0. The span equal to 0, the support and the deflection equal to 0. Where to substitute this equation? This equation should be substituted in a deflection equation. Substitute in deflection equation ei times 0. Then x equal to 0, c2 becomes 0. Now c2 value we got, for that is second constant of integration. After getting second constant of integration, then substitute at b. What is at b? X equal to L and y equal to 0. Again here another constant x equal to L and y equal to 0. Then we'll get it c1. The c1 value is minus ml by 3. So here the boundary conditions are considered related to the deflection, and there are two unknowns, c1 and c2, that means two constants of integration, and there are two boundary conditions. So that's why we got the c1 and c2 values. Substitute c1 and c2 values in the slope and deflections equations, then you will get the governing differential and slope equations of this case study. Now ei times dy by dx equal to, after substituting c1 and c2 in the above equations, the slope and deflection equations, the equation is obtained here minus mx square by 2l plus mx minus ml by 3, that is the c1. And whereas in deflection c1 and c2, here c1 and c2, here ei times minus mx cube by 6l plus m by 2 x square. Then if you substitute, okay, then c1x and c2x here, this is the final simplification we got. Now at slope at a, what is the slope at a? At x equal to 0. Substitute at x equal to 0, slope at a, that is at x equal to 0. Then the equation becomes minus ml by 3ei. Slope at b, at x equal to L. Then substitute in the slope equation here, in the equation of the slope, that is ml by 6ei. Okay, it is ml by 6ei. This is minus ml by 3ei. Alright, ml by 6ei and ml by 3ei. Now for the case of couple at one end, we have to find out the maximum deflection. How to find out the maximum deflection? The maximum deflection where the slope is 0. We are going to locate the deflection value. Okay, we are going to locate the deflection value. How to find out the maximum deflection? That location is required, x value. So make it a slope equation equal to 0. Make it the slope equation equal to 0, that is 3x square minus 6lx plus 2l square equal to 0. From that x value comes, the x value is that 0.423 times L, 0.423 times L value. So substitute this x value in the deflection equation, then y maximum equal to minus m by 6el times x cube minus 3lx square plus 2l square x. Okay, minus m by 6el times x cube minus 3lx square plus 2l square x. Now after substituting in the place of the x value, this is the y maximum here, 0.423l. If you substitute here, then the y maximum is obtained as minus of 0.664 ml square by 6ei. This is the maximum deflection for the case of couple at one end of a cantilever simply supported beam. Here, if you observe carefully, there is no concentrated load in the equations. W or UDL, small w doesn't appear. The moment is appear. The moment appears here, m appears here. If you upper couple, in the equation of slope at A, that is minus negative of ml by 3ei. In the case of slope at B, that is ml by 6ei. In the case of maximum deflection, that is 0.64 times ml square by 6ei. This M is the couple. So these equations, by looking at equations, we can know the couple is acting on the beam, and there is no UDL or uniformly distributed load, and also no concentrated load is acting on the beam. So here that is couple at one end. Now we covered so far the double integration method. By using double integration method, we calculated simply supported beams, slope and deflection of a simply supported beam subjected to concentrated load at midspan and uniformly distributed load throughout the span of the beam and couple at one end, and derived the formula for slope and deflections. Now in these equations, we are going to study the Macaulay's method, second method. The another method of Macaulay's method is known as method of singularity function. So what is the difference? What is the difference between double integration method and the Macaulay's method? So while applying the double integration method for different multiple concentrated loads, then we have to do number of equations. A separate expressions for the bending moment is needed and to be written for each section of the beam. So each producing a different equation with its own constants of integration. So that's why this method, double integration method is only highly convenient for simple cases. That's what we have seen. So far all cases are simple cases. If the multiple concentrated loads acts on the beam, then we have to go for the constant of integrations become C1 and C2, C3, C4 and so on. So for that, suppose if multiple concentrated loads are acting on the beam, then which method is best one? The Macaulay's method is highly useful, and in this Macaulay's method we will write only single equation. By using single equation, but that single equation is useful for throughout the span of the beam. And in that we make it the parts for different parts. Suppose if the three loads are acting, we make it the equation is such a way that it covers throughout the span of the beam. So let us begin with a overhanging beam subjected to multiple concentrated loads, that is W1, W2, W3 at various distances. So how to apply this Macaulay's method? In this Macaulay's method, EI times d square by dx square equal to, we consider a section at such a way that at a distance from W1 at sub point A, that is the origin, to E. So write down the moment equation, that is minus W1 times x plus R1 times x minus A minus W2 times x minus B plus minus W3 times x minus C. This equation covers throughout the span of the beam. If you want to consider AC portion, so first part you have to consider. So there is the parts are separated by separation lines. Now the portion to the left of the first separation, this is minus W1x, is valid for the portion of AC. Now minus W1x plus R1 times x minus A, that two portions is valid for the portion C to D. Next, up to the portion to the left, up to 1, 2, 3, this is up to here. This is AC portion. This is the portion is, if you want any slope and deflection between A to D, we have to consider this much portion of the moment equation. Now we want up to AE. AE we have to consider this much portion, 3 portions. Between that, if you want to derive the slope and deflections, now the complete equation is required if you want the slope and deflection between the portion EB. So, and while we have to integrate first integration, we have to add constant of integration only to the first portion. Let us begin. Now, integrate, we are considering here throughout the span of the beam. Integrate the first integration of this equation. EI times dy by dx equal to minus W1 times x square by 2 plus C1 plus R1 by 2 x minus a whole square minus W2 by 2 x minus b whole square minus W3 by 2 x minus c whole square. Now if you integrate again another one more time, that gives the deflection equation, that is minus W1 times x cube by 6 plus C1x plus C2 plus R1 by 6 x minus a whole cube minus W2 by 6 x minus b whole cube minus W3 by 6 x minus c whole cube. These two equations are known as the slope and deflection equations. This equation is the slope equation. This is the slope equation, and whereas this equation is known as the deflection equation. So for deflection equation, at various values of x, we can find out the deflections and slopes throughout the span of the beam. That is Macaulay's method. Coming to next method, there is moment area method or Morse theorem method. So this Morse theorem method is highly useful for the bending moment diagram consists of triangles and rectangles and squares. Otherwise, it is highly inconvenient for the bending moment diagram consists of parabolic curves or cubic polynomial curves. Why? Here the moment area method means it depends upon the area of the moment bending moment diagram and the centroid of the bending moment diagram from any other left support or right support. Now that's what this one here, it is inconvenient for the uniformly UDL loads when acts on the beam. Then the bending moment diagram becomes that is the quadratic equation, the parabola. So that there we have to consider the area of the bending moment diagram is difficult or inconvenient. That's why where for that type of case studies, you have to, that is the best method is called Macaulay's method. So this is the difference between what is the moment area method and Macaulay's method. Now by using this moment area method, we are going to explain it. There is a beam subject to some type of load. Then the bending moment diagram refers to here. An elemental distance, if we consider here the CD dash, C and D element, after bending it becomes a CD here, C dash and D dash. By C dash and D dash, if you draw the tangents, intersects point O, and that curve of is the radius of curvature is the R. The angle made between two tangents is d theta. It is also between two normals equal to d theta. Now if it is a dx, okay, is the reference line we considered here. So in terms of theta, if we derive it, that theta equal to A by EI. Theta equal to A by EI. What is the area of the bending moment diagram, where EI is the flexural rigidity. So this is the Morse first moment area theorem. So what is the Morse first moment area theorem? The difference of slopes between any 2 points on an elastic curve of a beam is equal to the difference of your slopes, that is theta LHS, that equal to net area of the bending moment diagram between these 2 points divided by flexural rigidity EI. That is the meaning of first. The second moment area theorem gives the deflection. So this y equal to a x bar by EI. What is the a? Again, moment area of the bending moment diagram. So what is the second moment theorem? That is called the intercepts on a given line between the tangents to the elastic curve of a beam at any 2 points is equal to net moment taken about the line of the area of the bending moment diagram between the 2 points, that is a x bar, divided by EI. What is the EI? Flexural rigidity. EI is known as flexural rigidity. Okay, this is what explanation here. This is the deflection. So area of there are 2 parameters are highly required. One is area bending moment diagram, another one is bar x. If you know, then we can calculate. That is theta equal to A by EI, and another one y equal to A x bar by EI. So these 2 things can be calculated. Now, for a case of cantilever beam, for the case of the cantilever beam, point load at the free end, that is the figure shows here. What is the theta maximum? Theta max equal to A by EI. What is the A? This is the case study. What is the area of the bending moment? This is the bending moment diagram. What is the area? That is the triangle of WL times L. That is theta maximum equal to A by EI, WL square by 2EI. We calculate it directly. Next, Y maximum, that is A x bar by EI. A we know. What is the bar x? It is at a distance of, if we consider x, that is 2/3. 2/3 by 2 by 3 times L. Substitute x bar x here and A value, that is WLQ by 3EI. This WLQ by 3EI, where it is? Y maximum, maximum deflection. And it is the theta maximum, that is WL square by 2EI, and Y maximum equal to WLQ by 3I. Like that, now for a concentrated load at any point, concentrated load at any point, point A is the throughout the span L. At point C, W is acting, fixed support is A, and B, free end support. Now theta maximum equal to A by EI. Now what is that A value? Of A times WA, we can understand here. Now that is WA square by 2. Substitute A value, that is WA square by 2EI. That is theta maximum. Now Y maximum equal to A x bar by EI. A, what is bar x? L minus A plus 2/3 of A. This is L minus A, the distance. From here to here we want bar x. L minus A plus 2/3 of A. Now substitute bar A value and bar x value and EI. Then we will get Y maximum equal to WAQ by 3I times 3I plus WA square by 2AI times L minus A. These are the values. A x bar by WA square by 2AI is the maximum slope for this case study. And maximum Y is WAQ by 3I plus WA square by 2AI times L minus A. So these are at a distance we want at the point of application of the load. What is the Y equal to WAQ by 3EI. So in this manner we have to calculate here cantilever beam with load is acting throughout the span of the beam. What is theta maximum? WLQ by 6EI, and Y maximum is WL power 4 by 8EI. Here A by EI is the generic formula, a generic equation. What is the A? Area of the bending moment diagram. We need area of the bending moment diagram. The area of the bending, this is the bending moment diagram area. So what is the area? 1/3 of BH. What is 1/3 of B? B is the L, H is WL square by 2, the maximum here. Then this value A by EI, that is WLQ by 6EI. What is AX bar by EI? What is the bar X? We know the A value is of 1 by 3 times. What is the A value? 1/3 BH, that is WLQ by 6. A value is WLQ by 6. Now we want bar X. What is the bar X? That is 3 by 4 times L. Substitute bar X value and A value in the equation of maximum deflection, that is A and X bar, then WL for 4 by 8EI. This is for UDL. Now coming to simply supported beam for concentrated load at the midspan. This is the area of the bending moment diagram. So what is the maximum value? WL by 4. Okay. Now how to make it start doing? We know that A by EI. What is the area of the bending moment diagram? Of L by 2 times WL by 4. That is between area of the bending moment diagram between A and C. WL square by 16. So substitute here A value and EI, WL square by 16 EI. That is the slope at A. So area of the bending moment diagram not throughout the span, between A and C we consider, that is half base into height. That is what here, half base, that is L by 2, height WL L by 4. Now Y maximum, where will be the Y maximum? At the mid span, that is A x bar by EI. What is the area value? A value WL square by 16, a bar x 2/3 of L by 2. Then Y maximum equal to WLQ by 48 EI. That is the maximum deflection at midspan. By using which method here? We are following moment area method. Moment area method. We are following here the moment area method and calculating. These are all moment area case studies. Similarly, apply the uniformly distributed load throughout the span of the beam. The bending, this is the curve, we got it, BMD. The area of the bending moment diagram, that is 2/3 times L by 2 times WL square by 8. Substitute in the place of A this value, area of the bending moment diagram, that is WL cube by 24 EI. How it comes here? Third of again 2/3 of BSH into H. Base is L by 2. This is L by 2 and this is WL square by 8. That is what we consider here. Now A x bar by EI. What is the bar x? A value you know, that is 5 by 8 times L by 2. Substitute here A value and x value by EI. That is 5 WL power 4 by 384 EI. We derived here already by using double integration method. Let us go back by using double integration method. UDL on the whole span. Yes, 5 by 384 times EI WL power 4 on the whole. Yes, that's for cantilever beam. Yeah, this is the equation. 5 by 384 EI WL cube by 24 EI. WL cube by, yes, 5 WL 4 by 384 EI. We already derived by using which method here? Previous methods, and here by using moment area method. By using moment area method, we got 5 WL 4 by 384 EI. It is validated. Now, the equations here, this slide indicates the various how to derive the various slope and deflections and maximum deflections of a cantilever beams. The cantilever beam is subjected to point load at the free end, and the point load is at the distance of A from the fixed support. And the third case is the UDL, uniformly distributed load, is acting throughout the span of the beam, and uniformly varying load is acting. So like that, these are the formulae which are highly important, prominent cases mentioned in this slide. Now here, the slope and deflections relationship, how the slope and deflections are having. Because we derived the formula by integrating the slope equation, we got the deflection. So there is a connection between slope and deflection. Here theta equal to, for this case, simply supported beam, theta equal to ML by EI. For this case study, what is the M here? The maximum couple here, first M is acting, ML by EI. Now the deflection comes maximum theta times L by 2, that is ML square by 2EI. The theta multiplied by L by 2, the slope multiplied by L by 2 will get ML square by 2, that is for deflection value. So similarly here, WL, M equal to what? Here WL square by ML by 2EI, where M is WL, that is WL square by 2EI. Then deflection comes theta times 2L by 3, then deflection value. These are the cases for 6 case studies mentioned, which are prominent to solve the problems directly, and also public service examinations. This formula is important. Now these are the different cases we have studied, and here the boundary conditions in this slide, it may not be visible, but the point is that at the boundary conditions, how at the different boundary conditions mentioned in this chart for a simply supported beam and cantilever beam. So in this session, we covered a Macaulay's method and solved some of the cases by using moment area method. And these are the books we followed, references, and also web references we followed in this session. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.